All right, so we talked about vaporization. We're taking liquid, turning it into the gas phase. So the heat of vaporization, right, like we talked about, because we're going to be breaking intermolecular forces, that is going to be an endothermic process. We're going to have to destabilize all those water molecules. Remember all that hydrogen bonding in water, right? You're going through, you're breaking all that up. So that's definitely going to require energy to happen. So heat of vaporization is the energy required to overcome those intermolecular forces. So it makes sense that the higher the intermolecular forces, the higher the boiling point, the higher the heat of vaporization. All of that, it makes sense that it's going to all go together. If we look at condensation, that's just the opposite, right? So if I take liquid water and I convert it to a gas, that is the heat of vaporization. And like we said, that's going to be a positive value. It's going to be endothermic. If I reverse that and I go from a gas to a liquid, right? Just like we did with Hess's law back in chapter 7, we know that if you reverse the reaction, your sign of delta H just flips. So in other words, if my heat of vaporization, let's just throw out a number, is 40 kilojoules per mole, then my heat of condensation is negative 40 kilojoules per mole. And that's not what I meant to put there. I meant to put equals a negative. All right, so I was going to say it's exothermic. So anyway, vaporizing is always going to be endothermic, whereas condensation is always going to be exothermic. Because when you take a gas and you put it into the liquid phase, you're forming intermolecular forces. And just like when you form bonds, that's going to release energy. If you're breaking intermolecular forces, just like you break bonds, it's going to require energy. So if it requires 40 kilojoules per mole to break up those bonds, it's going to release 40 kilojoules per mole to form those bonds. So the relationship of condensation and vaporization, just like we saw in Hess's law with chapter 7, it's the exact. We've just flipped it, right? So you just change the sign of delta H. Okay, so here are some questions that are going to bring us back to thermo. It says to vaporize. So we want to remember that means we're taking liquid to a gas, 1.50 grams of benzene. It requires 652 joules of heat. What is the heat of vaporization? So honestly, this is a Hess's law question, or not Hess's law. It's a thermochem question all over again. So we have C6H6 liquid becoming C6H6 gas. We are using 1.50 grams of benzene, and we are requiring 652 joules of heat, which means it's a reactant, and that makes sense because it's endothermic, right? It requires 652 joules to vaporize 1.50 grams of benzene. Now, we want to know the heat of vaporization, which is almost always going to be listed in kilojoules per mole. So what I know from this is it took 650, oh boy, I can't even write. So 652 joules of energy to vaporize 1.50 grams of that C6H6 benzene. So if I want to get this into moles, I need the molar mass here. So 12 carbons would be 72.06. Then we'd have another 6 hydrogens, 6.06. And all together, we have 78.12 grams per mole. All right, grams on top because we need it to cancel out, moles on the bottom because we need it per mole. Last thing I would do here is I know there's 1,000 joules in a kilojoule. Okay, so I'm going to take my 652 and divide that by 1.50, multiply that by 78.12, and then divide that by 1,000. And we'll go with 3 significant figures. So the heat of vaporization I get here is 34.0 kilojoules per mole. All right, so I had to kind of squeeze that over on the other side. So heat of vaporization for the benzene, 34 kilojoules per mole. So just kind of as an aside, kind of pushing this up here, that means that our heat of condensation for benzene would be negative 34 kilojoules per mole, right? Because those are just opposite, right? With Hess's law, if you reverse the reaction, you just change the sign. So back in thermo, we had questions like this where you had a chemical equation and it would say, okay, you get this much energy released, or it requires this much energy to react this much of whatever reactant it was. What's the enthalpy of the reaction in kilojoules per mole? We're doing the exact same thing again. We're trying, instead of enthalpy of reaction, we're specifically looking at the enthalpy of vaporization, which means we're changing it from a liquid to a gas, just one substance, no reaction, just a phase change. And you always take the amount of energy per amount of substance, and then just make sure your units end up in kilojoules per mole. So we have our energy of 652 joules required, so we know it's a positive. We have in the denominator our 1.50 grams of benzene, changing grams to moles using the molar mass from the periodic table, and then just changing joules to kilojoules using that prefix of 1,000. Kilo means 1,000. So 34 kilojoules per mole heat of vaporization for benzene. The condensation would just be the opposite of that. This question didn't ask for the heat of condensation. I just wanted to point it out since we talked about it on the last page. So next question, to vaporize, the heat of vaporization of ammonia, and I would tell you that's NH3. All right, the heat of vaporization in this case is given. It actually says the heat of vaporization is 23.4 kilojoules per mole. How much heat is required to vaporize 1 kilogram of ammonia? So an endothermic process means heat is on the reactant side, right? It's a positive delta H. It's an endothermic process. Heat is required for this to happen. I know I need 23.4 kilojoules for every mole of ammonia, but I don't have a mole, I have a kilogram. So the question is, how much heat am I going to need to do that 1 kilogram of ammonia? So just like we saw with chapter 7, if the heat of vaporization is given, this is going to be your conversion factor. So what I need to do first is take my kilogram of ammonia, change it to grams, and then change it to moles using molar mass. 1 nitrogen, 3 hydrogen, 17.04 grams per mole. So that's just the molar mass from the periodic table. So this would tell me how many moles I have. Then what I need to do, heat of vaporization, 23.4 kilojoules would be required for each mole of ammonia that I had. So I'm taking 1,000 grams, divided it by the 17.04 molar mass. I have about 58 moles of ammonia. If I need 23.4 kilojoules for every 1 mole, I would need, it says 1373, but if I round that to 3 sig figs, it would be 1370 kilojoules. That would be the amount of energy I would need to vaporize that kilogram of ammonia. So what you're going to notice in chapter 12 is there's a lot of chapter 7. So there's a lot of thermo here. We're just, instead of looking at chemical reactions, we're just focusing on phase changes. But a lot of the content that we learned in chapter 7 is going to come back. So here's another question that says, how much heat is released by liquefying or condensing a 52.7 liter container of ammonia at a certain pressure and temperature? So what I notice here is I have a gas, I've got a pressure, temperature, and a volume. So hopefully this reminds you of gas laws. And you're going to say, that kind of reminds me of, the question, do I use P1V1 or do I use PEVNERT? And we're not doing any kind of like looking at different sets of conditions. It's just, this is our volume, this is our pressure, this is our temperature. So we're going to use PEVNERT. And what we're going to do is first, we're going to find N. So I'm still looking at the ammonia. And if I want to find N, that would be PV divided by RT, pressure 0.987, the volume of 52.7 liters, R 0.08, 206, temperature 251. All right, so I'll take my 0.987, multiply it by 52.7, divide by 0.08, 206, and then also divide by 251. So I have about 2.5 moles of ammonia, but this is gas. All right. So these two questions are back to back on purpose. So if I just gave you this question on the quiz or the test or something like that, your heat of vaporization or heat of condensation would have to be given. I'm carrying it over. So it's almost like this is part A, part B. So like we're doing two different questions. But the heat of vaporization, we're still looking at ammonia, is 23.4 kilojoules per mole. So that would have to be given to you here. All right. So what I know is I've got 2.53 moles of ammonia gas. I know the heat of vaporization for ammonia is 23.4. We want to know how much heat is released by condensing or liquefying this many moles of ammonia gas. So like we were talking about, if I know that taking ammonia liquid to ammonia gas, heat of vaporization is 23.4, let's go the opposite direction. We have ammonia gas in this question becoming ammonia liquid. And that is the heat of condensation rather than vaporization. So that means it is negative 23.4 kilojoules per mole. So I'm going to release 23.4 kilojoules for every 1 mole of ammonia. And I found through PivNert that I've got about 2.5 moles of PivNert or of ammonia. So if I have 2.53 moles of NH3 gas, then what I'd set up is my conversion factor, negative 23.4 kilojoules for each mole of ammonia. So if I just kind of carry what I got on the calculator, keeping my 3 significant figures, I would have negative 59.1 kilojoules released. That would be my amount of energy released for that sample of ammonia gas. All right, so this one, again, it's really just thermo added to some gas laws. And the gas laws, I recognize anytime that says P, like anytime it gives you pressure, temperature, you know it's going to be gas laws problem, right? ATM, the only time we ever use that is gas laws. So, and it says gas, but I'm thinking, all right, P1V1 or PivNert, I got one volume, one pressure, one temperature, so PivNert. We use that to figure out how many moles of ammonia gas we had, right? We understand pressure, volume, temperature, so we can find our moles. And then if I know how much ammonia I have using that heat of condensation, then I can figure out my energy released. Now, again, heat of condensation is the same as heat of vaporization. We just changed the sign because we just flipped the reaction. So what you'll find in chapter 12, you're going to definitely have with chapter 12 a lot of thermo. All right, so Sophie, you may have to just watch the first part of the video again. Let's see. Need to use gas laws if we're going from a liquid to a gas. It is possible. So if you're going to go from a liquid to a gas, it could say something like, what if you're putting in this much energy, what volume of gas would you create at, I don't know, 746 torr and 23 degrees Celsius. So it could happen where anytime you're solving for the amount of gas, so in this case, we had gas, we were going to liquid, but what if we were taking liquid to gas? So instead of saying you have a kilogram of ammonia, what if it said, well, we had 500 kilojoules? Then what volume of ammonia could be created? So you could still have to do gas laws. Okay, so just to summarize here, your heat of vaporization, liquid to gas, condensation is going from gas to liquid. We just flipped the equation, so you just change the sign. So just carrying over, if your heat of vaporization right up here is 23.4, then your heat of condensation would be negative 23.4, right? We just changed the sign because we've just reversed the equation. Now, vapor pressure, we talked about that with the collected over water problems. So here's what happens with vapor pressure. Let's say I've got a beaker, and in that beaker, I have water in the liquid phase. So with the water, we understand high intermolecular forces, the water molecules in the body, right, connected to all the water molecules around it, right? Like, it's just highly ordered, high intermolecular forces. Then you get to the surface area where not as many intermolecular forces are there because there's just nothing on top. So those molecules at the surface, they vaporize first. All right. So what could start to happen, right, is those water molecules start to vaporize and go into the gas phase. But what you'll learn a lot about in Chem 2 is that molecules are constantly moving. And so for every reaction or change, in this case, physical change, you have the opposite change also occurring. Like every equation that we've ever written where we show it going to the right, truth is it also goes to the left. We just haven't talked about that. We don't until we get to Chem 2. And at some point you reach what's called dynamic equilibrium. Dynamic equilibrium is the point where those two opposite reactions are happening at the same rate. So in other words, the rate of vaporization is the same as the rate of condensation. So what does that mean? It means that it looks like nothing's changing, right? Because as quickly as it's vaporizing, it's recondensing. So when you get to that point of dynamic equilibrium, there is a little bit of water that's here in the gas phase. In other words, hydrogen steam, right? H2O in the gas phase. And that right there, those water molecules, that's the vapor pressure. Just a little bit of water in the gas phase above the body of the liquid. And what we noticed was vapor pressure for water was temperature dependent. The higher the temperature that you were at, the more molecules that would be sitting in the gas phase, the higher the vapor pressure, which makes sense. Boiling point, the actual definition of boiling point, is the temperature at which the vapor pressure above the liquid is equal to atmospheric pressure. So when the pressure of gas above the liquid, or the vapor pressure, equals the pressure in the room, you have reached boiling point. All right, so boiling point is that temperature at which the vapor pressure, the pressure of the molecules above the gas, equals atmospheric pressure, the pressure in the room. If it says that you have a normal boiling point, I always thought it should have said standard, because what that means is the atmospheric pressure is standard pressure, which is 1 atm. Okay, I don't know why normal. I would think standard. So when we say a boiling point of water is 373 Kelvin or 100 degrees Celsius, really that should be specifically referred to as the normal boiling point of water, or the standard boiling point, right? So what we know is, like, if you go up in altitude to Colorado, climb one of those mountains, and you're at 12,000 feet, the air is thin, right? So your atmospheric pressure is lower. So your boiling point is going to be lower, right? You're going to reach atmospheric pressure a lot sooner because your atmospheric pressure is really low. So if you're trying to boil pasta out in Denver, it's going to take you longer because you get to boiling point, which, let's say it's only like 92 degrees Celsius instead of 100 degrees Celsius. So that pasta is just not going to cook as quickly because it's sitting at a lower temperature. All right. So boiling point, again, temperature at which that vapor pressure sitting above the liquid is equal to the pressure in the atmosphere. And if it says normal boiling point, that means that pressure in the atmosphere is 1 atm. So what's going to happen now is we're going to learn a new equation, which is called the Clausius-Clapeyron equation. Our lab's going to look at this, our last lab. And it is natural log of P2 over P1 is equal to negative heat of vaporization over R, and then 1 over T2 minus 1 over T1. As we've talked about with those change in energy formulas, if you see this formula as inverse of T1 minus inverse of T2, then you won't have the negative here for the heat of vaporization. So sometimes you see it a little bit differently because if you flip the order of the temperatures, it'll change the sign in front of heat of vaporization. Now, this R is not the R we saw with gas laws of 0.08206. It's the energy R. That's what I used to always call it. And is 8.31 joule per mole Kelvin. So it's not the same 0.08206. So what will happen in lab is you'll actually have natural log of P. You're going to take vapor pressure data, and that'll be your y-axis. Your slope is going to be equal to heat of vaporization over R, and then inverse of T is going to be on the x-axis, and it makes a straight line equation. But we'll talk about that when we get to lab. But this is a new formula for us to look at. The algebra here might be slightly more complicated. This is where my my love for my calculator really came in because it requires the least amount of parentheses and steps for me to solve these problems. So I'll show you how to do it on my calculator. And then you may have to play around with it on your calculator just to see how your calculator wants to plug all this in. So I've got carbon disulfide, CS2, has a normal boiling point of 46 degrees Celsius, right? So normal boiling point means the temperature is 46 degrees Celsius when the pressure is 1 atm, right? Normal, standard. The heat of vaporization, okay, so that's our delta H of vaporization, is 26.8 kilojoules per mole. All right. We want to know what would the vapor pressure be, so this will be P2, when we're at a T2 of 35 degrees Celsius. All right. Now, no big surprise here. Temperature always has to be in Kelvin. So I'm going to follow the decimal place rule and I'm going to add 273 to each of these. So my T1 is really 319 Kelvin. My T2 is really 308 Kelvin. All right. So this is going to be Clausius-Clapeyron. We're going to plug everything in. So P2 is going to be my unknown. So I'm going to have Ln, P2 is my unknown. P1 is 1 atm, exactly 1, so 1.0000, won't limit my sig figs. And then I'm going to have negative heat of vaporization, 26.8 kilojoules per mole, divided by 8.31 joule per mole Kelvin. And then here I'd have the inverse of T2, 308, minus the inverse of T1, 319. Okay, so one thing I want you to notice is your heat of vaporization is always, almost always, it's in kilojoules per mole, and your R constant is in joules. So you're going to have to get those units to match first. So you can either multiply your heat of vaporization by 1,000, that's typically what I do, right? Or you could divide R by 1,000, but I usually just really quick right here is I put that factor of 1,000 there because that'll change my kilojoules to joules. So just don't forget that step. All right, you got to make sure and put that in. All right, so I'm going to try to do this piece by piece. I'm going to show you my calculator. All right, my calculator has the inverse key, so I love this calculator. So I'm going to type in 308 inverse, and then I'm going to subtract 319 inverse and hit enter. So the answer I get here, 0.000111957, right? And I'm just putting all the digits there just so you can see where my answer's coming from. So again, I did the parentheses first. I did 308 inverse minus 319 inverse, and then I hit enter. So don't forget to hit enter. All right. Some calculators don't want you to do it that way. You actually got to put in 1 divided by 308 minus 1 divided by 319. If you do that, you have to make sure to sort of think about parentheses, but this is your answer that you should be getting. Then over here, I'm going to take the negative 26.8. All right. Then I'm going to multiply it by 1,000. Don't forget to do that. And then I'm going to divide that by 8.31, the R constant. And the R constant, that's always that value. So it's always going to be 8.31 in the denominator. So I get here negative 3,225.03. All right, and I won't worry about the rest of it. That'll be enough digits. Okay, then over here, I cannot, this is key, you cannot break up the P2 and P1 until you get rid of the natural log function. We're not ready to do that yet. So I'm just going to leave the left side as is. Okay, so I'm not going to do anything to that just yet. So what I'm going to do is I'm going to take that negative 3,225 that's still in my calculator, and now I'm going to multiply by 0.000111957. So I get here negative 0.36106. All right, so nothing has changed over on the left side. All right, so after I took heat of vaporization times 1,000, divided it by R, and then multiply that by the difference of the inverse of T2 minus the inverse of T1, that's where I get this negative 0.36106. So I've solved for everything on the right. Now I can get rid of the natural log function. Okay, so you remember you cannot break up the parentheses until you remove the natural log function. Your calculator tells you the inverse of natural log is the e, the little e, not big E like exponent, little e, right? So I'm going to take e to both sides, which means natural log will cancel out because it's the opposite function. So I need e to that value. So my calculator, it understands what I want to do here. I have that value in my calculator, so I'm going to hit second and that button, and that gives me the answer. A lot of calculators, what you're going to have to do is you're going to have to put E and then to the negative 0.36106. Okay, so this is when I really started to love this calculator. So E to the negative 0.36106, I get 0.6969. All right, and if you want to add another, whatever, 3. Now I have P2 over 1 is equal to 0.69693. So now I can cross multiply the 1 ATM on both sides. And since it's just 1, right, that means your P2 is 0.69. We'll go with 3 sig figs, 7 atmospheres. Okay, and then at the end, I always like to ask myself, does that answer make sense? So when we were at boiling point, when the pressure was 1 atmosphere, we were at 319 Kelvin. We're at a lower temperature now. We're at 308. So we should be at a lower pressure. And we are. Instead of 1 ATM, we're at 0.7 roughly. Okay, so that's what Clausius-Clapeyron allows you to understand is if you know roughly the intermolecular forces and you know your normal boiling point, you can start predicting what the vapor pressure would be at different temperatures. And that's fine. The rounding part, it just depends. Like I will say with these questions, don't round like the inverse of temperature difference that we did here. Don't round that to 0.0001. You lose a lot of precision that way. I would try to keep at least 3 or 4 digits. And it's interesting with natural log function, or in this case, the E function, if you have 0.361, it'll change it. Not huge, but it is a little bit. So if your answer is going to, and you can imagine on the quiz, I'm definitely going to have to grade all these. If your answer is slightly different than mine, that's okay, but just slightly, shouldn't be huge. So if you got an answer here of 0.696 or 0.698, depending on how you round it, that'll be okay. All right, now next one, we've got selenium tetrafluoride. So SeF4 has a vapor pressure of 757 millimeters of mercury. So that would be my P1 at a temperature of 105 degrees Celsius. And it has a vapor pressure of 522 at a temperature of 95. All right. And we want to know in this case, what is our heat of vaporization? So we're still going to use Clausius-Clapeyron, but we're going to have to, in this case, solve for the heat of vaporization. That's what we want to find out. Now, with P2 and P1, in the last question, we were in atmospheres, and that was totally fine. And then in this question, we're in millimeters of mercury. Just like we did with Boyle's law, we have a P1 and a P2. As long as the units match, doesn't matter what scale I'm in. Okay, so we're going to leave this in millimeters of mercury to make our life easier. The temperature, as usual, has to be in Kelvin, right? So 105, this is really 378 Kelvin. And then the 95 would be 368 Kelvin. All right, so we have our 2 temperatures in Kelvin. We have our 2 pressures. Doesn't matter that it's in millimeters of mercury here. We need to solve for heat of vaporization. So our formula is Ln of P2, 522 millimeters of mercury, divided by P1, 757 millimeters of mercury, is equal to negative heat of vaporization. Don't know what that is, so we're going to leave that as an X. R, 8.31 joule per mole Kelvin. And then we'd have the inverse of T2, 368, minus the inverse of T1, 378. All right. Now, we don't have to worry about like not breaking up the natural log this time because we already have P1 and P2. So I'm going to go ahead and take 522 and divide that by 757. So I'm going to take the natural log of 0.68956 equals x, negative x, divided by 8.31. I'm not going to worry about the units, all right, until the end. And then let me go ahead and get what's in the parentheses or the brackets. So I got 368 inverse minus 378 inverse equals this difference 0.000071889. Okay, so again, on my calculator, I took 368 inverse minus 378 inverse equals. So I got 0.000071889. So that's my difference in the inverse temperatures. Okay, now back over here. All right, so the 522 divided by the 757, that's where I got the 0.68956 for. Now I'm going to take the natural log of that. So this answer gives me negative 0.371696. That would be equal to negative x over 8.31 times 0.000071889. Now, the negative and the negative, they're going to cancel out. So the negative and the negative will go away. That makes sense. Heat of vaporization has to be a positive value because it's endothermic. It has to always be positive. So let me put that little note over here. Heat of vaporization is always greater than 0. All right. So you have to get a positive value for heat of vaporization. If you don't, go back and double check real quick. So if I'm going to solve for x, I'm going to take the negative 0.371696. I'm going to cross multiply the 8.31. And then I'm going to cross divide the 0.000071889. And then of course, there's also this negative in here, right? That I'm flipping over for, because we want to get rid of that x, or sorry, the negative part of x. So the negative is going to cancel out. So I've got the 0.371696 still in there. Cross multiply the 8.31 negative. Oh, I forgot the negative. Sorry, that's okay. And then divide by 0.000071889. All right, and there's my value. Focus. So my x value, there we go. It says 42,966. But remember, the unit for R was in joules per mole. So if I divide that by 1,000 and I keep 3 significant figures, I'm going to have 43.0 kilojoules per mole. So my heat of vaporization, 43 kilojoules per mole. All right, so for selenium tetrafluoride, that's what we would be looking at. So just to kind of tie in some things here, what we talked about with intermolecular forces. This question we just did had a heat of vaporization of 43. The last example we looked at had a heat of vaporization much lower of 26.8. What's the difference? Okay, so selenium tetrafluoride, if you go through the Lewis structure, what you end up with here is selenium with 4 single bonded fluorines and 2 extra electrons to expand the octet. So it's an AX4E, which is seesaw. But without knowing the VSEPR, that's okay. What we know is that when you have that lone pair, the symmetry is gone. So what we have here is going to be a polar molecule. So this is going to have dispersion forces and dipole-dipole forces. If I go back to the last compound, we had carbon disulfide, which is a carbon center double bonded to 2 sulfurs. It is just a linear molecule. So carbon disulfide only has dispersion forces, no dipole-dipole, because the 2 sulfurs are pulling equally in opposite directions. So weaker forces lower heat of vaporization, which means that the vapor pressure will be higher at lower temperatures because it's easier to turn them into a gas phase. Down here, we have higher intermolecular forces because now we have polar dispersion forces and it's a heavier molecule. So we have higher heat of vaporization. All right, higher forces, higher heat of vaporization. So in terms of those trends, I don't know if I took that too quickly, sorry. Just to kind of summarize here, this is not the best place to do it because this doesn't match. What we're getting into doesn't match, but higher intermolecular forces. What that means is you're going to have higher heat of vaporization. We talked about that. We have higher surface tension, higher viscosity. But here's what's different. It will be lower vapor pressure. Right? The higher the intermolecular forces holding the molecules together, the less likely they're going to go into the gas phase, right? So higher forces, higher energy to change it from liquid to gas, higher forces, higher energy to break those forces to make surface area, higher forces, more resistant to flow, higher forces, less likely to be in the gas phase. Okay, so that's kind of a summary of some of the trends that we've seen with intermolecular forces. All right, now with solids, now instead of going from liquid to gas, we're thinking about solid to liquid, but it's going to be very much the same. So melting, fancy word there, fusion. Okay, so if we're going to take ice, solid, right, and convert it to a liquid, normally we call that melting. Okay, so what we're going to call it now is fusion. So that is going to be endothermic, right? Because we're still breaking forces. We've got the lattice structure of those ice crystals. We're breaking those intermolecular forces. Now we have flow, right? Same volume, but we have flow. So we broke forces, endothermic process. If I take liquid water and I freeze it, right? Now this is going to be called freezing or solidification. All right. That is instead going to be exo, right? And just like we saw with vaporization versus condensation, it's going to be the same value. It's just we're changing the sign. So if it takes 50 kilojoules to melt the ice, you're going to release 50 kilojoules when you freeze the water, right? If it's the same amount. So sublimation is what happens when you take, the example I always give is dry ice. So carbon dioxide solid, and you directly turn it into a gas. All right, so that's kind of fun. You don't pass liquid, you go right from solid to gas. That process is called sublimation. And again, it will be endo because we're breaking intermolecular forces. If I flip it and I take the gas and I turn it directly into a solid, that is called deposition. I kind of think of it like the gas deposits on the solid, right, in the solid phase. And since we're forming intermolecular forces there, that's going to be exothermic. All right, so this question, there's a question in the homework. It's a good question to do. It's also just kind of interesting, I think. So we've got a container of ice, and we're going to heat it until all the water has been evaporated. How much energy does that require? Okay, so what you have to think about here is, let's say I've got ice at negative 10 degrees Celsius, all right? And I want to take it to a gas at 110 degrees Celsius. What do I have to do? All right, a lot is the short answer. The first thing I'm going to have to do is take it to ice at 0 degrees Celsius. I've got to get it to the melting point. That is an MCAT problem. I have a delta T, right? I'm changing the temperature of the ice. Then what I'm going to have to do is I'm going to have to melt the ice into water. But I'm not going to change the temperature yet. I'm just doing a phase change. So that right there is the heat of fusion, right? I'm melting the ice. So delta H of fusion or delta H of melting. Then what I'm going to have to do is heat that water to boiling point. So I'm going to have to go to water at 0 degrees Celsius, or sorry, at 100 degrees Celsius. That again would be MCAT because I'm changing the temperature. Then what I'm going to do is I'm going to have to draw another arrow, is I'm going to take it to the gas at 100 degrees Celsius. That would be my heat of vaporization. So that's a delta H of vaporization problem because I'm changing the phase. And then after that, I can keep heating it if I want to and get to and use an MCAT formula. So when we're looking at this process, there are two possible things that are occurring, right? If you are changing the temperature, the state stays the same, then you use Q equals MC delta T. All right, so you can only change one thing at a time. So if we're going to change the temperature but keep the state the same, so we're taking solid water and just changing the temperature from -10 to 0, we would use MCAT. When I take water from 0 degrees Celsius to 100 degrees Celsius, the state doesn't change. I'm just changing the temperature, MCAT, right? But if I'm changing the state from solid to liquid or liquid to gas, then you use the same temperature. Temperature won't change. You use the heat of vaporization or sublimation or fuse, whatever it is that you're trying to accomplish there. All right, my computer froze real quick. There it is. Okay, so only one thing can change at a time, and it'll depend on that'll tell you what formula you're using. So if you're heating the substance, you want to use MCAT. If you're changing the state, you want to use delta H. Then again, you're heating the substance, you use MCAT. If you're melting or boiling, then you need to use the change in state, so delta H. So only one thing can change at each of those steps. All right. So let's take the water and think about the same process, but go in the opposite direction. So we're going to go from gas to solid. So if we start out with H2O gas at 100 degrees Celsius, that's the boiling point. Now we're going to cool it down, right? We're going to take it to liquid at 100 degrees Celsius, right? So we changed the state, but we didn't change the temperature. So what would we use there? Well, instead of vaporization, that would be the heat of condensation, right? If I take the water and continue to cool it, but now down to the freezing point of 0 degrees Celsius, then I'm going to use Q equals MC delta T. It's just Q is going to be negative because delta T is going to be negative. Then I can freeze it. I can take it to the solid at 0 degrees Celsius. All right, so temperature stays the same, state is changing, and that would be my delta H of freezing or solidification. All right, and then if I wanted to keep going and turn this into ice at -10 degrees Celsius, like the one I gave you above. So in this case, the state is staying the same. We're just changing the temperature. So again, Q equals MC delta T. Now here's the thing. When you do this problem, you have to be really careful because your heat capacity constant is state specific. So you have to make sure you use the correct C constant based on the state, whether you have ice, liquid, or steam. All right, so I just got to make sure you do that. All right, so there is a problem from the homework that I did. I'll get you the homework number in chapter 12 because it goes through all of these calculations. It's a really good one for you to practice. But before I can show you that, I got to look at phase diagrams, and I got to look at one other thing here first in our last 15 minutes. So a phase diagram. You'll have questions about this. This is another thing where it's sort of just conceptual. So the simple phase diagram, first thing is every molecule has its own, or every compound, I should say, has its own phase diagram. So everything has its unique phase diagram. So water looks a certain way, carbon dioxide looks a certain way. They're all different. So what you have on your phase diagram, that's supposed to be a straight line. is you have pressure and temperature. All right, when you look at the phase diagram for water, kind of start out with a curve here, and then this curve goes kind of slightly back, and then this one sort of goes like this. And if I kind of think about sort of drawing, let's say this is standard pressure of 1 atmosphere. Well, at low temperatures, right, you would expect that you have a solid, low temperature. If you keep heating, you're going to melt it. It'll turn into a liquid. And then if you keep heating it, it would be a gas. So this phase diagram is not perfect, especially because mine looks like it's crooked. But first thing you want to do is when you get your phase diagram, you want to label solid on the left, liquid in the middle of the Y, right? And then gas at the end. What this phase diagram would give you, in fact, I should probably just show you the one in the book because it looks a little bit better than mine, right? What this will tell you is this will show you, like, if you're at a certain pressure and a certain temperature, it'll tell you what phase you're in. So example, let's say we're at standard pressure and we're at about room temperature, right? Well, we know water is a liquid at room temperature. So I'm right around 20 degrees Celsius, right? Standard pressure. There's my liquid. If I go past 100 degrees Celsius at that same state, then I know I'm in the gas phase. If I'm lower than 0 degrees Celsius, the freezing point, then I know I've got ice. So every substance has a unique phase diagram. Makes sense because they all have their own melting point, boiling point, right? So what I need you to first see when you get a phase diagram is this part won't be labeled, right? So first thing I want you to do is go solids all the way on the left. Makes sense. Low temperature should be a solid. As you heat, it will liquefy. And then if you keep heating, it'll vaporize. So that's number one. Number two is let's identify what each of these curves represent. Okay, so the curve here, right? This separates solid from gas, right? Because this is the solid phase, this is the gas phase. So this right here would be the sublimation curve, or if we were going in the opposite direction, the deposition curve, right? Because that would be whether we're taking it from a solid to a gas or from a gas to a solid. But that's just what those names were called. The solid to the liquid, that was called, let me flip this sideways, that was called melting, but then the fancy word for that is fusion. And then to go from liquid to solid, that would be freezing, but fancy word for that is solidification. I don't personally love the fancy words. I would just call it freezing and melting, but whatever. Liquid to gas, we're talking about vaporization. And gas to liquid, we're talking about condensation. Those are those 6 phase changes that we've learned the names for. So we've got, again, solid on the left, liquid in the middle, gas on the right. All right, and the line this is called a curve, right? It's the sublimation curve because it separates solid to from gas. So we know right on this curve is where we transition from solid to gas, right? This curve up here separates solid and liquid. So that is the curve that separates that phase change of melting or freezing, depending on whether you're increasing temperature or lowering temperature. So that's what if it asks about the vaporization curve, that's what that means. It's that line that separates liquid from gas. Now, which of these steps are endothermic, which are exothermic? Well, we know that if you're melting something, you have to add heat. If you're boiling something, you have to add heat, right? You're breaking up intermolecular forces. So endothermic steps are when you go from solid to liquid to gas. So what are those called? Solid to liquid, right? We would call it melting, but the book would call it fusion. If we're taking liquid to gas, that's our vaporization. And if we're going solid directly to a gas, that is called sublimation. And that's the dry ice at Halloween. Exothermic is when we form intermolecular forces. So this is taking a gas to a liquid to a solid. So gas to a liquid, that would be condensation. Liquid to a solid we would probably call that freezing. But of course, we're going to call that solidification. All right. And then the opposite of sublimation is called deposition. All right. So when you are forming intermolecular forces, just like when you're forming bonds, you're going to release energy. It will be exothermic. When you are breaking intermolecular forces, that will be endothermic. All right. So the stronger the intermolecular forces are, you will have a higher heat of vaporization, a higher heat of fusion, a higher heat of sublimation. It just depends on what phase change you're doing, but it's all the same. So higher intermolecular forces, the more energy it will take to melt it. Higher intermolecular forces, the more energy it takes to vaporize it, right? So you see that. That also means higher boiling point, higher melting point if you're looking at solids. And again, like I wrote earlier, less vapor pressure. When you have higher forces, you have less molecules in the gas phase, so less vapor pressure. All right. So for the phase diagram question, it might say, okay, you're at, I'll say this temperature T1, and you're at this pressure. What phase is present at that temperature and pressure? So you'll have a phase diagram. You'll say, okay, let me go up here. We'll cross-reference it. Okay, at that temperature and pressure, I have a liquid, right? Or it might say you're at this pressure. Your temperature increases from this temperature to this temperature over here, right? T2. So what phase change would occur? Well, if I start out here, I'm in a liquid. And if I keep going, right, then I become a gas. So that would be vaporization. So those are the kinds of questions. You're really just reading the graph. There's a couple other things here. This intersection of all three curves, this is called the triple point, TP. All right, triple makes sense. All three curves come together. And what's fun about this is it is the temperature and pressure where all three phases coexist in equilibrium. So it is possible at a certain temperature, pressure to get ice, liquid, and gas all together in equilibrium. All right. And that would be true for any substance, but that's called the triple point. There's also a part out here, it's called the critical temperature. Don't worry about that. That's when you start making supercritical fluids, but we're not going to worry about that. So that's a phase diagram. Okay. So that was one other thing we had to talk about. Then a little bit more. We've talked a lot about intermolecular forces. I'm going to kind of summarize here on the next page. So to summarize intermolecular forces, right, we've got dispersion and everything. Add to that, polar molecules have dipole-dipole forces, and then hydrogen bonding adds an additional force when you have hydrogen bonded to nitrogen, oxygen, or fluorine. Those are forces between molecules. Now, forces within the molecule, right, holding the molecule itself together, don't worry about the neighbors, just worry about yourself. Those are ionic bonds, very, very strong, and then covalent bonds. So if we're just kind of looking at these forces, it makes sense. The molecule holds together really well. These intermolecular forces, they're strong, but they're not as strong as a bond or anything, right? So intermolecular versus intramolecular forces within. So you do not need to memorize these energies. I'm just curious. So I just thought it was a curious thing to know. All right, so now I've got a couple of substances here. Says we've got methanol and we've got fluoromethane. Boiling points are listed, which is which, right? So this classic. So the CH3OH, we've got carbon bonded to 3 hydrogens, bonded to an alcohol group. Remember that OH, that's telling you structurally that you have an oxygen bonded to a hydrogen. Okay, so that's our methanol. Then on the next one, we've got CH3 and then F. So the fluoromethane. Now, molecular weight here, 1216 is about 32. This one is about 35. Okay, so 34. Very similar in terms of molar mass, so we don't have to worry about that. So now let's look at what forces we have present. They both have dispersion because, of course, that's in everything. But since they're about the same molecular weight, that's not going to tell us the difference in the boiling point. They're both polar, so they both have dipole-dipole forces. The electronegative fluorine, right, is definitely going to create a negative side. So we're going to have a negative here, positive here. The oxygen, also electronegative, going to create a negative side and a positive side. So they both have dipole-dipole forces. So then the big difference is going to be that the methanol has the hydrogen bonding because that hydrogen is bonded to oxygen. But in the fluoromethane, that's not the case. The hydrogens are bonded to carbon, not to the fluorine. So yes, there's fluorine here, but the hydrogen isn't bonded to that. So this one doesn't have hydrogen bonding. So because the fluoromethane doesn't have hydrogen bonding, it has weaker intermolecular forces, no hydrogen bonds. That tells us the methanol has higher intermolecular forces. And what we learned was the higher the intermolecular forces, the higher the forces holding the molecule together, the harder it's going to be to boil it. So the boiling point of 65 degrees Celsius is going to go to the methanol. The boiling point of negative 78 degrees Celsius is going to go to the fluoromethane. Much lower boiling point because it doesn't have those hydrogen bonds. All right. So one more way to kind of summarize, we've got 3 compounds here. Let's list all the possible intermolecular forces. I'm going to start with carbon dioxide because we're used to seeing this one. Carbon in the middle, double bonded to 2 oxygens. It's a linear structure, non-polar, so dispersion only. In the SO2, after you do your formal charges, you end up with sulfur double bonded to 2 oxygens and a lone pair. So now this is going to be a bent molecule. We've lost the symmetry. So now we have dispersion forces and we have dipole-dipole. Those more electronegative oxygens are going to pull the electron density down away from the sulfur. Then we got butanol. All right, butanol, we've got 4 carbons. And on that last carbon, we have an alcohol group. Okay, so we know we have dispersion here because that's in everything. The electronegative oxygen is creating a polar molecule, so we also have dipole-dipole forces. And then, of course, on top of that now we have hydrogen bonds because of that alcohol, that OH group. All right. And again, everything attached to the carbon, I just drew the little lines because what you do in organic, because you get tired of writing hydrogen. These are all hydrogens that are attached. All right, so we identified all the possible intermolecular forces. Now let's put them in order of increasing boiling point. So which one of these has the lowest boiling point? Lowest boiling point would be the one that has the weakest intermolecular forces. That should be the CO2. All right. Next, in the middle would be the SO2. And then at the end, the highest boiling point, because it has the highest intermolecular forces, should be the butanol, the C4H9OH. All right, so that's a summary of what we talked about with intermolecular forces. And I finished almost right on time. I am like a minute late, but what I wanted to do here really quick is I'm going to go into the chapter 12 folder and I'm going to tell you that problem. If I don't have it at the ready, I'll email it to you, but there's a problem in chapter 12 that goes through those calculations of, you know, taking ice at negative 10 degrees Celsius and turning it into steam at 110 degrees Celsius. Let's see. So if you, I'm going to share my screen here really quick. If you go into the chapter 12 folder in my courses, you'll see this example of a heating curve problem. That would be a good problem to do. And it's just like what I was talking about. And in the homework, the chapter 12 answer key, the problem that I was talking about, it's towards the end. I think it's on the last page. Yeah, it's this one. It's number 77. So I'm going to write that on my notes here really quick. So the chapter 12 homework, make sure you do number 77, or at least practice it, because that'll go through all those calculations. If you need the answer key, it'll show you how to do it. But remember that if you are changing temperature, but you can't change the phase, you can only do one thing at a time. If you change temperature, it's MCAT. When you change the phase, the temperature stays the same, and that's when you use your phase change delta H. So that's the big thing with those questions, is to remember, are you using MCAT or are you using delta H? All right, so definitely in the TRO homework for chapter 7, make sure and look at number 77. It's a really good problem, but there is also that heating curve problem for water. That video is also posted in there. So definitely look at those to help practice those. It's nothing new. I mean, it's everything we did in thermo. It's just putting a lot of pieces into one puzzle. So it's like, instead of doing a 100-piece jigsaw puzzle, you're doing a 1,000-piece jigsaw puzzle. You can do it. It's just more pieces, more steps to think about. All right, so that's it. That's it for the semester. That's the last new material we have. So when I see you back on Tuesday, you will have completed your last credit quiz for chapter 11. That'll be due Monday at midnight. We're going to review for test 3 on Tuesday. Thursday next week, I won't see you because you're going to be taking the test 3. And then I'll see you the week after that on Tuesday to review for the final exam. So if you have any questions for me, let me know. But otherwise, I wish you a great weekend.